Friends, welcome to the Boolean Brain in continuation to the LeetCode Daily Challenge series, where we are solving the daily challenges from LeetCode. As you can see, today is 18th of January. Let us try to solve today's problem statement. The title says largest magic square. A k by k magic square is a k by k grid filled with integers such that every row sum, every column sum, and both diagonal sums are all equal. The integers in the magic square do not have to be distinct. Okay, every one by one grid is trivially a magic square. Okay, so we have given m by an integer grid. We have to return basically the size, that is the side length of k of largest magic square that can be found within this grid. Okay, again a problem with square has appeared in the daily LeetCode challenge series. If you are following the entire series, you can see that this is around fourth or fifth day where problem statement on square has been provided to us. So, in today's problem statement, let us try to understand this with help of this example. So we have given this grid and we have to basically return the largest magic square that can be found. So magic square is nothing but a square whose sum of all the rows, sum of all the columns and sum of its diagonals is exactly same. Then we can call a given square as a magical square. And we have to return the basically side length. We don't have to return the area, we have to return the side length. So in order to do this, let us try to understand the constraints. You can see M and N are the rows on columns of the given grid, and the constraints are mn less than 50. So since the constraints are very less, we I think we can go ahead with the brute force approach where we can start and try for all the possible squares starting from each location, and whenever we get the maximum length square that can get updated. Since there might be 3 to 4 loops that might involve, but considering the constraints, this brute force approach seems to be accepted. Let us try to code it. Try all possible squares. Okay, this is the brute force. And since we are trying all possible squares, in what is the condition that we are doing? We are trying the sum of all the rows and columns. So in order to do that, we can instead of calculating each row and each column sum repetitively, uh, in order to optimize it, we can use the prefix technique. So we can uh, store all the lengths of, we can store the sum of all the rows and columns using the prefix sum, and then we can basically optimize the last inner loop. But looking at the constraints, we will just try to code it up using the brute force technique. So this problem is not a difficult problem, it's just a lengthier problem implementation. Hence, the difficulty level is also medium. So let us try to code it live. First, we need M and N. So M is nothing but total rows, and N denotes the total number of columns. Okay. We also declare answer whose initial assigned value would be 1 because of answer is assigned to 1 because any cell at a given point of time can contribute to the magic square, right? Because it is satisfying all the conditions of every row, every column, and both diagonal sums are equal. So answer is assigned to 1. Now, in order to find all possible squares, we have to basically start iterating on each of the cell. So if we can assume of something like top left corner of a square this, so we can go consider this one as the individual square, then the next one is this, then the next one is this, and the next one is 4 size, this. So that's how we have to basically move. So we have to start from each cell. So I starting from 0, I less than n, I plus plus, int j equals to 0, j less than n, j plus plus. Okay. Now this is nothing but the starting point of each cell. But again, from each cell, we have to go in size. So initially, one for one we don't need to do. we can start from 2. We can check if the size of 2 contributes to the answer. If not, we can check for size 3. We can check for size 4. So I need a k. So let me introduce another loop for k initially assigned to 2 and k is less than equals to. So and before, in order to find the limiting range constraint for k, I need to figure out max size. So for what is the maximum size of square that can form from each cell? So that is nothing but minimum of total number of minimum of total columns front of it and total rows in front of it, right? So that comes to m minus I and n minus j, right? So if we are starting from here, we only have 3 rows to go. So max square that can form is of size 3. So that's where we define a size and update it here. Okay, cool. Now we are starting from k assigned to 2. K is less than equals to the max size and k plus plus. Okay, cool. Now let us now the condition is that all the row sum, column sum, and diagonal sum should be equal, right? So let's define a variable target to store that value. Also, we will introduce a flag magic, which is initially assigned to true, and this will be used to denote a specific cell with a specific square of size k is magic or not, right? So that's for that tracking that we declare this magic. Now we first try to go calculate the first row sum in order to update the target, right? So for calculating the first row sum, I will start from C, declare a C loop. C is initially assigned to value J and C is less than J plus K because J is denoting my column, alright? So C is assigned to J. I want to start from this column. I want to go till J plus Kth column and K plus plus. Why J plus K? Because K is denoting my size of squares. Okay, cool. Now I want to update my target initially with first row sum, grid of uh, ith row and cth column. Okay, cool. I now have the updated target with me. Now I want to check if the current target is if this current is meeting for all the rows, right? So I check for all the rows and r equals to I because I'm at the ith row and j column. So I want to go for the rows below this, right? So r starting from I, and r is basically less than I plus k, and what we can do. Since let's say we initially computed sum for one row, and while computing the sum for next, we want to check if this is matching to our row, right? So that's how we can basically avoid looping further. So I have this magic. So I'll update the condition to ensure magic is also true and r plus plus. Okay. So we are starting a loop for all the rows from I to r less than I plus k. Again, why k? Because k is the size. So if you're starting from here, we only want to, for k equals to 2, we only want to come till this row, not beyond further it. So I plus k and magic is the condition for unnecessarily looping further, even if some target is not met, and we increase the r. Now, in each iteration, we need initially take the declare row sum to 0 and try to calculate the sum for entire uh, columns, so all the columns, all the cells in current rth row. So C initially assigned to J. Why J? Because J is my um, column starting, and I want to go till J plus K. The way in which we updated only till K, because K is the size, we also want to go till K, right? And C plus plus. Cool. Now I want to update, sorry, yeah, I want to update the row sum. Row sum plus equals to read of what should be the R. I will coordinates R and the inner loop C. Okay. Now I have the row sum with me, and in order to update the magic, what I can do, if row sum is not equals to target, this target is this. If the current row sum obtained is not equals, then we can basically assign magic to false. Okay, cool. Now similarly, I want to check for all columns. In order to, the way we did for rows, we want to consider adding for all the columns. So for calculating all the columns, we again start the loop. Initially C assigned to J, and C is less than J plus K C plus plus. We again declare a column sum now, initial assigned to 0. We start another loop for iterating all the cells in the current column. So in R equals to I, R less than I plus K, R plus plus. I will try to update the column sum grade of C and sorry, R C. Okay, yeah, because I want to come down, right? So I want to, the inner loop is for the row and the outer is for the columns. So I starting from I position, I till I plus K, I plus plus, and we update the column sum here. Okay, good. Now, the similar condition if, okay, I think I forgot to add magic. Okay, because this will help us reduce some extra loops. Now, I need to check if the column sum is not equals to target, right? Then magic equals to false. Cool. Yeah. Now we want to calculate the diagonals. Yeah. So we went ahead with all the rows. We went ahead with all the columns. Now we want to calculate the diagonals. So in order to calculate the diagonals, let me declare two diagonal initially assigned to 0, and I am starting another loop where in D initially assigned to 0 and D is less than K. Again K because I want to only go till sides. D plus plus. Okay. Let us update the diagonal 1. So diagonal 1 will come to the grade of I plus D. Okay. We want to come till this way. So I plus D. Okay. And for the column, it should be, column was denoted for J, so it should be j plus d. So we iterated in the column wise, row wise as well as column wise. Row of I plus t plus j plus t. Okay. Similarly, we try to update the diagonal 2. Diagonal 2 again equals to read of I plus t. We want to increase the row, and in order to calculate the mm, you want to calculate the from reverse, right? So what we can do, mm, it should be I plus t, and the column should be j plus k, the total size, and adding the total size minus basically d and 1. So d is basically the diagonally range that you want to go, like the size of square, you can say. So I want to update that, right? Cool. Now, once the diagonals are also computed, we can add a condition to check if the diagonal 1 is not equals to target and diagonal 2 is not equals to target, magic is equals to false. Okay, we just try to update the magic. If magic answer equals to max of answer comma k. Why k? Because if you carefully observe, we are iterating on the kth loop. So kth loop basically is for the squares. So my bool is true. The Boolean magic is true till end of this. Then it means that is the potential answer for updating the k. Okay. So yeah, I think this is it. Let us try to run this. Okay. Some columns mistake. Okay. Mhm. Yeah, sample test cases are passing. Let us try to submit this. Yeah, cool. It's successfully accepted, right? So let us try to improve the check the time and space complexity of this. So if you carefully observe, we are running these two loops, right? So it is m into n. Apart from that, for each cell, we are running another loop. We are running another loop of size 2 to till k, right? So into k. Okay. Now for each k size, where k is the size, what we are doing, we are again trying to figure out all the sum of elements in the first row, then all rows. So this is basically one loop. So linear complexity of O of k. This is checking all rows. So it is having two loops. So k into k square. Similarly for columns, we are having two loops, k square. This is the linear time complexity. So eventually it is k into k square, which eventually goes to k cube. Okay. Yeah, so I think this is the time complexity of this. And in terms of space complexity, we are not using any extra space. So it is O of 1. Okay, so this is for the brute force approach. But if you observe for the um, uh, uh, optimize approach, we can basically, instead of calculating this internal loops, right? So we can get this in O of 1 if we pre-calculate those values and store it in an array using prefix sum. So space complexity will increase, but definitely the time complexity will reduce by one loop. It should be an O of m. Again, if this k is really nearing to n, so what is the constant for mn? It's 50 only, right? So again, yeah. So maybe m into n into k square into n into k square. Okay, so till this point we might decrease the complexity, but this is the entire solution. Cool. Yeah, I hope you understood the problem statement and the solution. This is nothing but a simple ad hoc implementation problem where this kind of problems are little lengthy. You just the only expectation out of such problems is you are able to identify and implement the logic. So since we implemented the brute force logic only, right? So this is the skill that one checks when this question is basically asked. Okay. Cool. Then, if you're still watching here, please consider giving this video a thumbs up. And if you're new to the channel, please to consider subscribing. Thank you so much.